Hello everyone. In the last class, we have discussed about the response of undamped and damped systems to free and forced vibrations. Under forced vibration, we have seen the response of those systems under sinusoidal loading. Today in this class, we will discuss about how do single degree of freedom systems respond to seismic excitations. When it comes to seismic excitations, we have this single degree of freedom system shown over here, which is excited by the ground displacement given over here as UG, which is a function of time. Let us say that the mass of the system is m and the stiffness and damping are represented by k and c respectively. The total displacement of this mass is given by ut, which is again a function of time. Now here we have to define a few quantities before we derive the equation of motion based on D'Alembert's principle. So here we have two entities, one is our absolute motion and another is our relative motion. How are these defined? Let us try to understand. So the absolute displacement of this mass is given by ut, which is a function of time. So the absolute velocity will be given as u dot t and the absolute acceleration will be given as u double dot t, whereas the ground motion is represented by displacement ug, velocity u dot g and acceleration u double dot g. Now in order to obtain the relative motion of this single degree of freedom system, we have to subtract the ground motion from the absolute motion, which means relative displacement is given by u as ut minus ug. Similarly, the relative velocity u dot shall be given as u dot t minus u dot g and relative acceleration u double dot as u double dot t minus u double dot g. Now this arithmetic is valid only for linear systems. That's how we are able to subtract the ground motion from the absolute motion to obtain the relative motion. At this point, we have to be clear that the stiffness force in this structural system will be obtained using the structural deformation, which means it will be obtained using the relative motion. At this point, we have to understand that the stiffness force in the structural system will be obtained using the structural deformation. And what is a structural deformation? The structural deformation is the relative motion of the single degree of freedom system with respect to the ground, which means that the stiffness force will be given by stiffness k multiplied with ut minus ug. Alright, because the deformation in the stiffness element is ut minus ug. At the same time, the damping force will be given by the product of damping coefficient c and the relative velocity, which was u dot t minus u dot g. But at the same time, the mass has an absolute motion given by displacement ut, which is a function of time, and the inertia force originates because of the mass of the body. Therefore, the inertia force is actually m times of the acceleration of the body in absolute terms, which means the inertial force is m times of u double dot t. Now we have the stiffness force, damping force and the inertial force known to us. We can write the equation of motion using D'Alembert's principle as over here. It will be m times of u double dot t, which is the inertial force, plus the damping force, which is c times of u dot t minus u dot g, and stiffness force plus stiffness force, which is k times of ut minus ug, equal to 0. Now since the excitation is in the form of the ground vibration, we are not having any force which is explicitly applied on the body. So that's why the right hand side term is equal to 0. Now there are two ways to express this. If we do further simplification in terms of ut, u dot t and u double dot t, we get the equation as mu double dot t plus c u dot t plus KUT equals CU dot G plus KUG. If we want to know the value of the displacement, velocity or acceleration of this mass, or in this case the absolute motion, that is ut, u dot t and u double dot t, then we need to know the values of u dot g and ug. But the acceleration, but the ground motion is expressed in form of acceleration time history. So we do not know what is the ground displacement and what is the ground velocity unless we are performing the integration. That's why this type of expression is difficult to solve. Now we will express the same equation in terms of relative entities. So here ut minus ug becomes equal to u and u dot t minus u dot g becomes equal to u dot, and mu double dot t we can represent it as m times of u double dot plus u double dot g. So if we do the simplification, we get this expression as mu double dot plus cu dot plus ku equals minus mu double dot g. So in this equation we get only one term on the right hand side, which is minus mass times of the ground acceleration, and since the ground motion is given to us in the form of acceleration time history, this is very amenable. We will be able to solve this equation quite conveniently. Further, we are more interested in understanding or knowing what is the structural deformation rather than absolute displacement. Why? Because structural deformation leads to damage in structures. It is not the absolute motion which leads to damage in the structure. Suppose if a structure has the same motion as the ground, so the structure members are not deformed and thereby there will be no damage. Okay, so that's why we are more interested into relative displacement, velocity and acceleration of the structure, and that's why we are more interested in this equation. Okay, once we have obtained the equation of motion for seismic excitation, now let us look into some of the responses of structural systems during earthquakes. Okay, so in this slide we have 6 numbers of single degree of freedom systems whose response has been evaluated when they are subjected to L centro ground motion. We have earlier seen L centro ground motion is one of the most widely used ground motions in understanding seismic response or performing seismic design of building structures. So the left hand panel, these 3 are corresponding to single degree of freedom systems with the same amount of damping, that is 2%, but different natural period. The right hand side panel shows 3 single degree of freedom systems which have the same natural period of 2 seconds, but the damping is increasing as we move from top to bottom. So what do we observe from these seismic responses? Again, these responses are shown in terms of structural deformation on the y axis, and on the x axis it is the running time of the ground motion. So let us try to decode what do we understand from these plots. One thing is very clear, that as the natural period of the system changes, the period of vibration of these single degree of freedom systems also changes. The period of vibration of any of these single degree of freedom system is very close to its natural period, irrespective of damping. For example, the single degree of freedom system with natural period of 2 seconds has a period of vibration which is roughly 2 seconds, if you carefully observe in this plot. Okay, we have earlier seen in the last class that the damped vibration of any structure occurs at damped natural frequency or damped natural period, which is slightly different to the undamped natural frequency or the undamped natural period. Okay, second thing which is evident from these plots is that the longer natural periods are often associated with large deformations, which means that while this single degree of freedom system with natural period of 0.5 seconds has a small peak in the structural deformation. The single degree of freedom system with natural period of 2 seconds has a larger peak. Okay. Another thing which we observe from these plots is that as we increase the damping in the system, the systems respond much lesser. That is, the heavily damped systems, that is the system with more damping, respond less compared to lightly damped systems. Okay, out of all these observations, what is clear to us or what is evident is that the response of single degree of freedom system is largely characterized by its natural period and damping. Another observation is that the peak deformation, that information about peak deformation is very important because it defines what is the likelihood of structural damage and what would be the internal resisting force, as we will see later. So, therefore, we need to understand what is the peak value, and therefore, we need to plot the peak value of any response quantity. So, from these observations we come to the concept of response spectrum, where we plot the peak value of a response quantity. In this case, we were trying to obtain the deformation. It can be any other response quantity, and this is plotted as a function of natural period or a related parameter. It can be natural frequency as well, and it is drawn for a certain damping ratio. Now, what do we infer from this? For example, we have 3 single degree of freedom systems over here. Each of them has 2% damping, but the natural period is varying at 0.5 seconds, 1 second and 2 seconds. These plots are for structural deformations for these single degree of freedom systems subjected to L centro ground motion, and are very similar to these plots as we have seen. We will decode what is the peak value from these plots, and we will plot them as a function of natural period, which means on the x axis we have natural period and on the y axis we have the peak values of these structural deformations, the peak absolute value to be precise, and this is provided that all of these single degree of freedom systems have the same damping. So, if we plot them, what we get is the response spectrum for structural deformation. Okay, on the x axis we can also have natural period, we can also have natural frequency in lieu of natural period, but in that case, but since structural engineers are more conversant with natural period, you will find most of the plots which have natural period on the x axis. Now, we will look into various steps that are involved in construction of response spectrum. So, the first step would be to numerically define the ground acceleration, that is, we should have the ground acceleration time data. After defining the ground acceleration, we will select a single degree of freedom system with a given natural period and a given damping ratio. For that single degree of freedom system, we will compute the deformation response. For that single degree of freedom system, we will compute the deformation response and we will identify its peak absolute value. That peak value will be identified as D. Now, we will define 2 more quantities, and one of them is V, which is omega n times of D, that is the natural frequency, that is the cyclic natural frequency multiplied with D, and the second quantity is A, which is cyclic natural frequency multiplied with V, or the square of cyclic natural frequency omega n square multiplied with D. Now, these quantities are respectively called as pseudo velocity and pseudo acceleration. These are not the real values of velocity and acceleration of the single degree of freedom system, they are slightly different from them. In this case, we have just defined them by these products. We will understand why defining pseudo velocity and pseudo acceleration helps us in obtaining the design seismic load. Okay, after obtaining the value of D, V and A for that single degree of freedom system, we will repeat the steps 2 to 4 for other single degree of freedom systems with the with varying values of natural period and damping ratio, and we will consider all the values corresponding to single degree of freedom systems having the same damping ratio and plot them to obtain the spectral ordinate, and then we will plot the obtained spectral ordinates for varying natural period on the x axis and one line for a given damping value, and then we will plot the obtained spectral ordinates as shown alongside, where different spectral lines will be drawn for different damping values. In these figures we have shown only one spectral line, which means it represents the variation in natural period, but the damping essentially remains constant for all the systems. Okay. If we have system with other damping value, they will be represented by a different line on the same plot. Now, once we have understood construction of response spectrum, we should be aware that the same process may be repeated for other quantities such as actual velocity of the structure, actual acceleration of the structure, such as absolute or relative velocity and acceleration, energy dissipation, etc. Now, we will look into some of the most widely used response spectra in seismic design. By now, we have been already familiar with D, V and A, which are deformation, pseudo velocity and pseudo acceleration response spectra. So, these three response spectra D, V and A are the most commonly used response spectra in our seismic design. Why are they important? Let us try to understand. The deformation response spectrum gives us information about the peak structural deformation, and which represents the likelihood of damage. In this slide, we have also given how a typical D, V and A spectra look like. So, if you closely observe the D spectra, that is the deformation response spectrum, in this case for rigid structures, that is for structures with low natural periods, the value of D is almost 0. The value of D is almost equal to 0. For flexible structure, on the other hand, D approaches a value which is equal to the peak ground displacement. The pseudo velocity response spectrum provides information about the peak pseudo velocity, and if you carefully observe, if we multiply it with half of the seismic mass, we shall be able to get the value of peak strain energy. If we multiply the square of the peak pseudo velocity V with the half of seismic mass, we shall get the peak strain energy or peak energy dissipated by the structure. So, that is why it is important to understand how the pseudo velocity response spectrum looks like. For rigid structures, the pseudo velocity response spectrum has a value of 0. For flexible structures, that is structures with large natural periods, the pseudo velocity response spectrum approaches peak ground velocity. The pseudo acceleration response spectrum provides us information about the peak pseudo acceleration, which can be multiplied with seismic mass of the structure to obtain the peak base shear, which is further used in design. So, the pseudo acceleration response spectrum for rigid structures is roughly equal to the peak ground acceleration, and for flexible structure it diminishes to approximately 0. And by now, so if you are further curious into these spectra, you should look into a book on dynamics of structures. Now, once we have these response spectra known to us, we should understand that these three spectra essentially contain the same information, because we have defined pseudo velocity and pseudo acceleration arithmetically from the deformation. So, once we have this equation, that is v equals omega n times of t and a equals omega n times of v, what we can write them in logarithmic terms by taking logarithm on both the sides of these equations, as log d will be given by log v minus log of 2 pi by Tn, and log a will be given by log v plus log of 2 pi by Tn. Tn is the natural period, which is Tn is the natural period, and omega n is the cyclic natural frequency. Omega n is equal to 2 pi by Tn. Once you have these equations, it can be deduced from these equations that we can plot each of these three quantities d, v and a on the same graph, with the axis of d and a inclined at 45 degree and 135 degree respectively, while the axis for pseudo velocity, that is v, is on the vertical axis. Okay, so once we are able to plot all of these quantities on the same plot, this plot is called the tripartite plot, and the relevant information may be obtained directly from this plot, which means if we have, suppose we have a single degree of freedom system with natural period of 2 seconds, and we go to the plot, from here we can say what would be the value of peak deformation, peak velocity and peak acceleration. Okay, so let us try to now, let us try to understand what are the different characteristics of response spectrum. Once we have the tripartite plot, we see that for any tripartite plot for rigid structures, the value of pseudo acceleration remains nearly constant. As you can see, this is the pseudo acceleration axis, and the pseudo acceleration value remains nearly constant for rigid structures. For intermediate structures, the pseudo velocity remains nearly constant, and for flexible structures, the pseudo displacement remains nearly constant, as this is the axis for pseudo displacement, which means we can tell that the rigid structures lie in the acceleration sensitive zone, the intermediate structures lie in the velocity sensitive region, and the flexible structures lie in displacement sensitive regions. Okay, now let us try to understand how do we obtain a design response spectrum, because ultimately we need to design our structures, for which we need to obtain the design response spectrum. So, the first step would be to obtain site specific ground motions based on regional seismicity, earthquake sources in the vicinity, site soil conditions and historical seismic data. Based on the historical seismicity of the region, we shall be able to obtain site specific ground motions. More comments on this will be available in further lectures. Okay, after obtaining these ground motions, we will obtain response spectrum plots for a given damping ratio corresponding to different ground motions, which means on the same plot of the response spectrum, we shall have different plots corresponding to different ground motions. If we take 30 ground motions, we shall have 30 different lines on the same plot. We will obtain their average value across the plots and then smoothen the average plot to obtain the design response spectrum. This process is most simplified way to obtain the design response spectrum. However, the design response spectrum, which has been arrived in different building codes across globe, follows little complicated process, for which you can always refer to any book on structural dynamics. So, in the upcoming class, we will look into how do we find the design seismic load on any building structure. Thank you.